So we were discussing that first, if we write the energy form, okay, all terms are in joule. But in general, we put it as a rate equation. So all we have to do is to put the dot symbol. So we are doing the derivative with time. So then it will be delta E over delta T. And then because it's joule per second, then we are getting the all terms in watt. So we have rates. So rate of energy stored plus sum of rate of heat plus sum of rate of work W dot plus sum of m dot n en, so the mass flow rate coming in bringing energy, minus sum of m dot out e out. Okay, now how we can combine terms in order to include the enthalpy. This is what we call the internal energy. Okay, and the internal energy is decomposed, or this is the energy, sorry, the total energy of the particles coming in and getting out. So this energy is decomposed into several parts. You can write it as internal energy plus kinetic energy plus potential energy, etc. In majority of mechanical equipments, turbines, pumps, okay, the variation of internal energy is dominant over kinetic and potential. This is why in several problems they tell you neglect the change in kinetic energy and potential energy. And if they don't tell you this and you are able to calculate them, you can do it. And you can see that there will be negligible compared to the change in internal energy. Okay. So this is why in general, they are very small, we neglect them. If I give you the velocity at the inlet and the outlet, no need to neglect. You can calculate it and see the amount of this energy compared to internal. Okay. Now, concerning the heat and work, this will be given for you. And as I can tell you, for example, you have loss from the turbine to the surrounding by this amount. So we can include it in the equation. And also in general, for example, for a turbine or a pump, if they don't mention anything, we can consider that we can neglect heat losses to the surrounding. Okay, so also we can drop this term. But it's not always the case. So it depends on the problems I give. Okay, now why we have in mind in from thermodynamics that in general we use what we call the enthalpy, not the internal energy. Why? Because of this. First, the enthalpy is a property that we defined by combining several properties. Since we know that enthalpy H is U, okay, plus PV. And why we use the enthalpy? Because when we do the derivation here that we'll do together, this term will appear. Okay, you know that if H is U plus PV, then you have that DH is DU, okay, plus PDV, okay, plus VDP, okay. Now, in general, here, when you have a fluid, let's say, that is coming in and then that is getting out, you have pressure forces. You have pressure forces, and the pressure forces will do work. Okay, you know that the work of pressure is what, you know that for a force the work is force times distance. Okay, and we know that the force is a pressure times an area. So when we do PA times D, we can say that the work of pressure is pressure times volume. Okay. And then for when we consider, let's say, this, we know already that the work is related to change in volume. This is why we say that dW, okay, so elementary work is PDV. So here, whenever you have a flux coming in and getting out, you have work developed. You have a work developed at the boundary. Okay, and so already when you compute sum of works here, you should add the work at the boundary, and this work will include the term. Okay, will include the term of integral PDV. So for a small, if we do the analysis for a small amount of work, you have the term PDV. Okay, while when you account for the change in internal energy here, you also have to add. So here you have, let's say, m dot n PDV, because the flow coming in will do a positive work, and the flow getting out will lead to a negative work, because at the inlet you have the pressure and the velocity in same direction. So this will lead to a work done on the system. While on the exit, you have pressure forces opposing the flux that is going out. Okay, so we'll have a negative work. So you should do minus m dot out PDV, and of course you integrate to get the total work. On the other hand, okay, for UN here, you have that the fluxes coming in will include the term m dot nun. Okay, and for the one getting out, you have minus m dot out u out. So we can group these two terms. Okay, if we group them, you will see that this term du plus pdv can be combined together. Okay, to be replaced by dh. Okay, vdp, especially when we consider liquid, is very small, so we will consider this, will neglect this term, and we have that dh can be calculated as du plus pdv. This is why in such problems you can replace, if you want, the work of pressure forces plus m dot nun minus m dot out u out by m dot nhn minus m dot out h out. So from here, the enthalpy term. Okay. In addition, in case we have any source of heat and work, we should take it in consideration. So if we take the simple example of the turbine, what can we say? So for our turbine, okay, we have the flux, we have energy flux coming in, energy flux getting out. We neglected any heat loss to the surrounding, so we just have W dot turbine, which is out. So if I want to write the equation, dE by dt, which is the storage term, and also if they tell you we have steady state case, so if we deal with the problem in steady state conditions, dE by dt will be 0. So no storage term if you have steady state problem. Steady state means no change with time. So dE by dt is equal to minus W dot turbine, minus because I'm losing this work. So minus W dot turbine plus M dot NHN. So this is, if you want, we are lumping here the energy and the work done at the inlet. So plus M dot NHN minus M dot out H out equals to 0. And you know that when you have steady state, okay, no storage of mass, so M dot N is equal to M dot out. Okay, so from continuity equation, so minus M dot out H out. You can say because of steady state, okay? So from steady state also I can say that M dot N is equal to M dot out. So I can deduce the work of the turbine. So I applied for this open system, okay? I applied my first law of thermodynamics, and I was able to relate the work produced by the turbine to the change in enthalpy. Okay, and this is an introduction for next chapter. In next chapter, we'll study power plants. Okay, so how we can convert heat into work. Okay, so we just have here equals to m dot times hn minus h out. Okay, we'll see in next chapter several types of power plants and how we can increase their efficiency. Okay, now going back to a closed system. So if we consider now an overall system, which is, let's say, a refrigeration system. Okay, I will give you an example of a cycle that will be used to refrigeration, or it will be used as a heat pump. So we already talked about power cycles. In power cycles, we provide heat to produce work. In refrigeration or heat pump cycles, okay, we provide work in order to cause transfer of heat in a way opposing the natural one. What do I mean by this? So in conventional cases, we know already from heat transfer that we'll always have heat exchange from hot temperatures to cold temperatures. But if you want to force, okay, if you want to force your system to work in the opposite way, you want heat to go from a cold to hot place, okay, you need to do external intervention. And this can be done through a heat pump or refrigeration cycle. It consists mainly, an example of this cycle is the easiest one, is formed by an evaporator. So we already gave an example of power plant, which is of a power cycle, sorry, which is the case of internal combustion engine. We can also have, if you want, cycles, power cycles that will, and they are used a lot to produce electricity through power plants. You can circulate, let's say, air through a series of steps, okay, and it will have, you will have the same components that will draw now. We'll see that the components of a refrigeration or heat pump or a power cycle are very similar to each other. The only difference is how we circulate the refrigerant or fluid, and we'll discuss this now. So if you consider, for example, an evaporator, then a turbine, we'll see that one main difference between power cycles and refrigerant ones is here. If you want to produce work, you put a turbine. Okay. If you want to operate your cycle as a power, as a, when you want to produce work, use a turbine. Okay. When you want to have refrigeration purpose, you want to, let's say, put, you don't want to have a loss of work through a turbine, you should put an expansion valve. Okay. So we'll discuss in a while the difference. You have also the condenser. And you have the compressor or pump. It depends. If you have a gas, okay, or if you have a liquid. So pumps mainly are used for liquids, while compressors are used for gases. So pump or compressor. Okay. Now, what is the idea and how we can switch from a refrigeration or heat pump cycle to a power cycle? First, if your purpose is to produce electricity, for example, okay, then you need a turbine, because the turbine will, at the level of the turbine, you will get W dot out, okay, and this W dot out can be converted to electrical power, because the turbine will rotate the shaft, and the mechanical energy can drive a generator, and then you can produce electricity. Okay, so this is W dot out. If you want to do this, then you should circulate your fluid in this direction. So what will happen? You have first let us say the evaporator. What will happen at the evaporator level? The evaporator level is a heat exchanger in which your fluid will gain heat. So as the name indicates, you have evaporation process. Evaporation process is related to heat gain. So your fluid should gain heat. So here we have Qn. Now, what can be the source of this heat input? You can have several possibilities. Okay, you can have combustion of fuels. You can have, let's say, it depends on the application. Okay, you can have solar power, for example, that can supply Qn, etc. So you can have several possibilities. The important is that you should supply heat at this level. So we supply heat at the evaporator level, then your fluid is heated. The internal energy of it will increase. Once it will reach enough energy level, it will get out of your evaporator. It will get out of your evaporator and pass through the turbine. In the turbine, as we discussed in a while, the enthalpy, which represents the energy carried by this fluid plus the effect of pressure, will be transformed into work because the enthalpy will decrease as you go through the turbine and you will release energy in form of work to the outer environment. So you are producing work. Okay, but you can tell me why we use this cycle. Okay, we produced work. Why we need this cycle? Because we'll see that it's never possible to produce work from heat 100%. Yani you can never convert heat 100% into work. What will happen, you will always have a certain part of heat that is lost. Okay, so this is why what we will do here to operate this cycle in a continuous way, after the fluid will get out from the turbine, now it's at a lower energy state, but we need to repeat, and in order to be able to repeat the process, we need to bring it back to the state where where it entered the evaporator. Okay, to do so, we should pass it first through a condenser, as the name indicates here, and the condenser will have rejection of heat. So Q is out. Okay, and we'll see when we study in detail the cycles next time. We'll see why we should pass the fluid through the condenser, okay, in order to reach the state where we can pump it or compress it. So it depends if it's liquid or a gas. So in the condenser, what will happen at a constant pressure, we will reject heat. So we have condensation process, heat is rejected. And then at the exit of the condenser, our fluid will be ready to be pumped or compressed. So the pressure will increase again to be able to reach a state where it can enter the evaporator. So in overall, at the evaporator level, we have heat coming in. At the condenser level, we have heat that is getting out. And at the turbine level, we have production of work, while in the pump or compressor, we have W dot N. Okay, so now in this mode of operation, what will happen is that I will supply, sorry, 1 minute. I will supply heat at the evaporator level to produce work at the turbine level. So this type of a cycle is a power cycle. And as we discussed before, we can calculate its efficiency. It's similar, if you want, to this internal combustion engine, but in the internal combustion engine, it's a if you have, let's say, a certain mass, okay, and this mass is undergoing this change within the cylinder. Here we have a fluid flow that is going through different mechanical equipments. Okay, so if I take each equipment separately, I have an open system. But if I join these 4 open systems, I get a cycle. Okay, where in this cycle operation, I can transform heat into part of work that is useful, and of course into another part that I might not need. And here, for example, here Q out is a loss. But if we use heat recovery, so if I can use efficiently this Q dot out, I can increase a lot the efficiency of my system. How? So if I just take this cycle alone, I can say that the efficiency of this power cycle is W dot out. But look, I cannot just say W dot out because I need also to lose a small part of it to drive the pump or compressor. This is why we say that we consider the network produced. So W dot out minus W dot in, which is the net useful power, over the heat input, which is Q dot in. Okay. And of course, the thermal efficiency is always smaller than 1. Why? Because for this cycle, I can say that sum of Q dot N, so sum of Q dot equal to sum of W dot. Okay. And if I take the convention that we are taking, I should put minus sum of W dot because we are considering everything getting in plus and everything getting out minus. Okay. So I can write that at the end, Q dot N plus Q dot out sorry, minus Q dot out because I am losing Q dot out, okay, equals to W dot out minus W dot in. Okay, now, as you can see here, always the net power W dot out minus W dot in is smaller than Q dot in because we have the heat loss Q dot out. And one very important way to enhance this efficiency is to use heat recovery. What do we mean by this? So this heat from the flow rate exiting the condenser, you can have gases, for example, that will enter the condenser and will take energy from the fluid. These gases, when exhausted, instead of being lost, we can pass them through another heat exchanger, for example, for another power plant. Okay, so always we can try to benefit from this loss. And if we do so, of course, maybe we'll not be able to recover it 100%, but if you recover a big percentage of it, you can increase the efficiency. So, and the overall efficiency of the system will be increased because you will use part of the loss that will be an input to another cycle. And we'll learn together how we can calculate combined efficiencies of combined cycles in next chapter. Okay. So now, if I consider this system, but now I want to operate it in another mode. Okay, I don't want to have a power cycle. I want to have a refrigeration cycle. Basically, it's the same mode of operation, but now uh, what is my input is here. I provide work as input. So this is the case of HVAC systems. You know that HVAC systems work on electrical power. So I can supply work in form of electrical power. Okay. And when I circulate my fluid, what will happen? You know, for example, at the evaporator level, you have, let's say, the evaporator is in contact with a medium of high temperature, T hot, okay? While the condenser will be in contact with an environment of lower temperature, T cold. So when I move my fluid, because I put electrical power to drive my pump, okay, this pump will elevate the pressure of my fluid. Then when it will enter the evaporator at high pressure and temperature, it will be able to extract heat from my medium here. So it will extract heat from an environment at T hot. And then it will pass, after passing by the expansion valve, when it will go through the condenser, it will reject heat to a medium of lower temperature. So I forced heat to go from a hot place to a cool place by imposing work at the pump level by delivering work in which is in electrical form to my pump or compressor. And why we don't use turbines in this case? Because turbine will take work out of my system. And here my purpose is not to produce work. My purpose is to transfer heat from hot to cold places. This is why I can replace the turbine by an expansion valve, and we'll see together that the expansion valve will nearly يعني I can neglect any W dot out from it. I can consider it nearly zero. It's a device that works at constant enthalpy. So it will expand my fluid while having constant enthalpy. So Hn equals to H out. And therefore, in this system, I was able to uh, displace heat from hot to cool environment by providing work. And I can operate this system in two ways. I can use it as a refrigerator to cool my room or as the heat pump to warm my room. So for example, in summer, your room will be from the evaporator side because your HVAC system, okay, uh, will operate in this way. It will circulate the fluid in a way that the room is from the side of the evaporator. So when the fluid will circulate, it will take heat from your room and it will reject it at the condenser level. And the condenser level is the unit that is outside of your room. You can see this machines that you put outside of the space, okay, and from the outdoor side. This one will reject heat during summer, okay. So you were able to reject heat from your inner space, which is relatively cooler than your outer space, because you supplied electrical work. Now, in case of winter, you reverse the operation of the system. Your room will be from the condenser side. So in this case, you will what you will do, you will reject heat into your room, okay, while you will take heat from the outer environment, which is in this case you are forcing heat to go from the hot to the cool place. Sorry, from the cool to the hot place. Okay, so it depends on what is your season. You can decide if you want to operate your system as refrigeration or heat pump. And if you want to calculate like a performance index, we have what we call coefficient of performance. Okay, COP. So your COP for refrigerant systems, you say, when I want to have a refrigeration application, what do I care for? I want to cool my room. I want to extract heat from it. So I will put it on the side of my evaporator. Okay? Because I want to put it from the side of my evaporators, and what I care for is Q dot N. This is my useful heat, okay? Because I want to extract Q dot N from the room to give it to the fluid. So COP refrigeration is Q dot N, which is the useful heat here, over my input. And my input is the electrical work, of course, that I put on my HVAC system. So it's W dot electric. So in case of summer, this is how I calculate the COP of my system. While in winter, I want to reject heat to my room. يعني heat that should be out of my condenser should be given to the room. So my room will be from this side because I will reverse the operation of my HVAC system in a way now that heat rejection will be towards my room. Okay. And in this case, the COP of heating is equal to the useful heat rate, which is Q dot out, that I will take to my room, over W dot electric. Okay. And of course, COP heating is always larger than COP refrigeration. Why? Let us just summarize again what we have. So we said that for a refrigeration or heat pump application, I provide electricity, W dot electric, to my HVAC system, and my HVAC system will force heat to go from hot place, so from T hot, from cold, sorry, from T cold to T hot, okay? Because as we mentioned, so here in the evaporator, what will happen? The evaporator, I will take heat, Q dot N, and in the condenser, I will have heat rejection. Pay attention for something, okay? When I say Qn or Q out here, when I say Qn or Q out, Qn is towards my fluid, okay? So Qn, my fluid will gain this heat, but my environment will lose it, okay? My environment will lose Qn. This is why we say that in summer, okay, my room should be from this side. Why? Because I will transfer heat from my room to my fluid, which is circulating in the HVAC system. Okay, so I want to take heat from my room and in order to cool it. Okay, this is why we say that for summer COP refrigeration is the heat extracted from the room through the evaporator. So it's Qn, Q dot N over W dot electric. Okay, while when I want to benefit from heat, okay, I want to pump heat, I say that COP heat pump so I want to put my room from the side of Q dot out to benefit from this heat rejection. So it's Q dot out over W dot electric. Now, if I want to relate COP refrigeration to COP heat pump, to relate them, what should I do? I can study in overall the overall balance of heat and work to my cycle. For my whole cycle, we said that for the expansion valve, we can neglect W dot, okay? So if I take my whole cycle, what can I write? I can write that Q dot N plus W dot electric equals to Q dot out. So always Q dot out is larger than Q dot N. Okay, so if I replace in COP heat pump, in COP of the heat pump, if I replace Q dot out by Q dot N plus W electric, so Q dot N plus W dot electric over W dot electric I obtain that the COP of the heat pump is equal to Q dot N over W dot electric plus 1. And Q dot N over W dot electric is the COP of refrigeration. This is why the COP of heat pump is always larger than the coefficient of performance for refrigeration cycle. Okay. So here I can operate my system depending on the season as heat pump or refrigeration. And by providing electrical work, I will force heat, okay, to go in the opposite direction of the natural one. In natural cases, heat will always flow from hot to cold. But with this system, I can force heat to go in the opposite way from cold to hot. Okay. And we'll see in detail how we can draw these cycles and how we can determine at different points what are the characteristics and how we can calculate efficiencies, COP, etc. Any question on this? So if you want this, what we did today is a combination of chapter 2 and 3. Because in chapter 2, we introduce the first law of thermodynamics at the end of the chapter. And we discuss, let's say, some ideal cycles like Carnot cycle. We have seen here some applications for open and closed systems. And in next chapter, we'll go into detail how we study these cycles, how we can increase the efficiencies of such systems, etc. Any question before we stop?
No, thank you.
Okay, thank you. Bye.
Thank you, Professor.
Welcome. Bye.
See you tomorrow.
Okay, bye.
Thank you, Professor.
Welcome.